Air behaves as a dense physical fluid. Any object moving through the atmosphere must physically displace millions of microscopic molecules every second. This diagram shows an aircraft in unaccelerated, straight and level flight. In this state, the forces acting on the aircraft frame are in perfect mathematical balance. The power plant's forward thrust exactly counters the rearward drag, and the upward lift exactly matches the downward pull of weight. To maintain that equilibrium, the aircraft has to generate its own upward force. It does this by driving horizontally through the atmosphere, forcing the motionless air to flow over the structure. This creates what we call the relative wind. By shaping the wings into precise geometric profiles known as airfoils, engineers dictate exactly how that relative wind behaves as it passes by. Flight is the active management of a continuous mechanical conflict, a physical war between the energy expended to move forward and the vertical force extracted from the air. We measure the success of that conflict using the lift-to-drag ratio. This cross-section illustrates the free stream flow, air moving without obstruction, approaching the leading edge of an airfoil. Right at the front, there is a specific location where the airflow meets the structure head-on, called the forward stagnation point. At this exact spot, the air molecules slam into the metal and stop. The local velocity drops to zero. Because that kinetic energy has to go somewhere, the absolute static pressure peaks, equaling the total pressure of the airstream. Because the upper surface of the wing is curved, or cambered, the air dividing over the top has to travel faster to keep up with the flow underneath. According to Bernoulli's principle, as the velocity of that fluid increases, its static pressure drops, creating a zone of suction above the wing. The higher pressure moving slower beneath the wing pushes upward toward that low-pressure vacuum. 3/4 of the total lift comes directly from the suction on the upper surface, while the impact of air on the lower surface provides the remaining 25%. The airplane is pulled up just as much as it is pushed. Lift is the strict, measurable net mechanical force resulting from that pressure differential. Because air has internal friction, or viscosity, it resists flowing smoothly over a solid object. The layer of air in immediate contact with the wing is slowed to a relative velocity of near zero. This localized zone of retarded airflow is the boundary layer. Near the leading edge, this boundary layer is incredibly thin. The air travels in parallel, orderly sheets sliding smoothly over one another. This is laminar flow, and it generates very little skin friction. But as the air moves further back along the wing, friction forces dissipate the stream's energy. A waviness develops in the layers, eventually growing so severe that the smooth laminar structure breaks down entirely in a transition region. The flow then becomes a turbulent boundary layer. The air particles mix aggressively, exchanging energy between layers. While this thicker, turbulent flow creates a much sharper velocity gradient at the surface, and therefore higher friction, it also pulls high-velocity, high-kinetic energy air much closer to the skin of the aircraft. Designers willingly accept the penalty of that higher friction drag. Without the added kinetic energy of the turbulent boundary layer, the airflow lacks the momentum required to stay attached to the curve of the wing. Any physical object moving through the atmosphere pays a penalty for displacing the air. We categorize this resistance as parasite drag, a force completely independent of lift generation. As the flat plate pushes through the air, the flow separates at the sharp trailing edges, leaving a low-pressure wake behind it. The high pressure up front pushes the object backward into that wake. This is form drag. Smoothing the shape into a teardrop profile allows the streamlines to close in cleanly behind the object, drastically reducing the wake. Then there is skin friction drag. This is the direct result of the viscous boundary layer, the scraping of air molecules against the microscopic roughness of the aircraft's surface. When two distinct surfaces meet, like where the wing joins the fuselage, their individual high-speed airflows are forced to mix in a restricted physical space. This creates a turbulent bottleneck and localized shockwaves known as interference drag. Those are the parasitic forces, but there is another penalty intrinsically tied to the creation of lift itself, induced drag. Because the pressure beneath the wing is higher than the pressure above it, the air naturally tries to escape upward. It bleeds around the ends of the wings, setting up a violent span-wise whirlpool. These wingtip vortices are the physical manifestation of induced drag. They constantly pull energy away from the aircraft. Every ounce of lift an airplane generates exacts a physical toll. Aerodynamics is an exercise in damage control, balancing the shape of the aircraft to minimize these combined dragging forces. We dictate how much lift is generated by changing the geometry of the flow. This diagram shows the angle of attack, which is strictly the acute angle measured between the incoming relative wind and the straight chord line of the wing. All the individual pressure variations across the wing surface sum together into a single resultant force. The focal point where that net force intersects the chord line is the center of pressure. As the pilot pitches the nose up, increasing the angle of attack, the low-pressure suction zone grows stronger. The lift vector increases in magnitude, and the center of pressure travels forward along the chord line. But there is a strict geometric limit. If the angle becomes too steep, the air simply cannot make the sharp turn over the leading edge to follow the upper camber. This is the critical angle, or the burble point. The smooth boundary layer violently detaches from the skin. The low-pressure vacuum is instantly replaced by turbulent, swirling eddies. The resultant lift vector collapses and form drag spikes. The wing is stalled. The burble point represents the absolute physical limit of the airfoil's geometry to manipulate the fluid medium. This chart plots out the complex variables of fluid dynamics. Aerodynamicists model the total lifting capability of an airfoil as the lift coefficient and its total resistance as the drag coefficient, graphing both against the angle of attack. By dividing the lift coefficient by the drag coefficient, we find the lift-to-drag ratio. This curve represents the airfoil's efficiency, the exact amount of drag the airframe pays to purchase its lift. Notice that the curve reaches a distinct peak. This is L/D max. Operating the aircraft at this exact angle of attack yields the absolute minimum total drag for the amount of lift being generated. If you pitch the nose lower, you lose lift faster than you shed drag. Pitch the nose higher, and induced drag begins to compound rapidly. Any deviation from this specific angle mathematically destroys the aircraft's efficiency. Aerodynamic design, piloting, and maintenance all converge on a single priority: preserving the geometries and surface conditions that allow the aircraft to reliably exploit that exact point of maximum efficiency.